Alright class, so we're going to talk about water's life-supporting properties. Alright, so to explain all the unique properties that water as a molecule possesses, you need to understand the chemical structure of water. Alright, so here in this diagram, you have an image of a water molecule. Alright, notice that looking at one end of the water molecule, you have the oxygen atom, which is more highly electronegative. Alright, so the electrons are pulled towards the oxygen atom. Alright, it has a stronger attraction of those electrons. And your hydrogen atoms end up with this partial positive charge. So in this case, you end up with a negative end and a positive end. Alright, so water is a polar molecule because of what's going on here and here. Right? The water molecule has two poles. Alright, so water is able to form hydrogen bonds with other water molecules. Alright, so you have an oxygen atom, which is interacting with a hydrogen on another water molecule, alright, through a type of chemical bond called a hydrogen bond. Okay. And water molecules are capable of bonding with numerous other water molecules through hydrogen bonding. Right, so this little bitty partial positive charge here can interact with another oxygen with a partial negative charge. And so on. Alright, so water, molecule of water has a very unique shape. Alright, it has a nice V shape. Alright, the top of the V, you have the oxygen atom. Alright, it's got two pairs of electrons up top. Alright, so it's already highly electronegative. Then you have your little hydrogen atoms, which are going to now be having a partial positive charge. Alright, so this gives the molecule of water a very specific symmetry. Alright, so when you're talking about water, alright, water has the ability to stick to other water molecules. We call this process cohesion. The ability of water molecules to stick to something else, and call it adhesion. Alright, so here you have a droplet of water that is sticking to the surface of a leaf. Alright, that droplet is able to adhere to the surface because of the adhesive nature of water. Alright, so again, cohesion, adhesion. Alright, so here you have an image of two water molecules that are holding hands. Alright, so the ability of water molecules to hold on to one another, alright, to bond to one another, is cohesion. The ability of water molecules to bind to some other substance, alright, is referred to as adhesion. Alright, so it could be as simply as water binding to the inner surface of a glass, like in a cup, drinking cup, or a test tube, or graduated cylinder. Alright, here you're being shown water molecules that are forming and breaking hydrogen bonds. Alright, so hydrogen bonds are not static chemical bonds. Alright, they don't always form and stay that way. Alright, they're going to form and break and form and break. So water is a liquid. The water molecules themselves have their own vibrations, and they're moving around in a solution in a container, and they're colliding with one another and forming bonds and colliding with other parts of the container, and they're breaking apart. So hydrogen bonds form and break. Alright, so looking at an application of this process of the adhesion and cohesion of water. Alright, so here we have a process of something we call transpiration. Alright, transpiration is the method by which plants pull water molecules from the roots up through the shoot to the top of the tree. Alright, so what's taking place is on the surface of the leaves you have these openings. Right, these openings are what we refer to as stomatas or stoma. They're basically nothing more than pores. Okay, and so here, when these pores open, all right, water molecules that are in the vasculature of the leaf are going to escape. They're going to evaporate, and as they evaporate, all right, you have this chain of water molecules that exist in the vasculature of the plant. All right, you have a particular type of tissue type. All right, you have xylem that's transporting water, all right, to all different parts of the plant. And so your water molecules are all adhered to one another in this vasculature. And so when one evaporates, one gets pulled up in a chain. And so when one gets pulled up and evaporates, it pulls other water molecules below it up. Water molecules will also adhere to the inner surface of the vasculature. Right? So it's this cohesive and adhesive nature that allows water to move against the force of gravity. So the water can be transported up to the top of a tree or a shrub. And down here in the roots, all right, water is being absorbed from the soil, all right, through a process of diffusion and osmosis of water molecules. All right, so when you look at the adhesive and cohesive nature of water, water also has something that we call surface tension. Alright, it's like all liquids. Alright, so in this case, water has a high surface tension. Alright, so what's taking place on the surface of a cup, on the surface of a swimming pool, on the surface of a pond, alright, you have your water molecules that they're touching this, they're at the surface, alright, and they're interacting with what's above it, air. Alright, so the water molecules aren't bonding to the air particles, alright. The water molecules are going to bind to one another along the surface much more strongly. Alright, they create this barrier. It's almost like a netting, if you will. All right. And below, they form hydrogen bonds with other water molecules. All right, but those below form hydrogen bonds with those above and next to them and below them. All right, so it's a little bit weaker of an interaction. All right, so it's strongest along the surface. All right, so it's kind of like a net or a trampoline. All right, so you can bounce and it has a little bit of a give. Okay, and it all has to do with the hydrogen bonds that are being formed between neighboring water molecules and how strong those attractive forces are to one another. All right, so it's high surface tension. This high surface tension is what allows for water to beat up on its surface. This is what allows for things like insects to walk across the surface of a swimming pool or pond. Here you have mosquitoes that are hanging underneath the surface of the pond. All right, it all has to do with the surface tension and ability to break the surface. All right. Water also has a high specific heat. But before we talk about specific heat, let's talk about heat and let's talk about temperature. Okay, the two are not synonymous. All right, a lot of times people will confuse the two and they'll use the words interchangeably. But heat is actually the vibration and the movement of water molecules. All right, molecules inherently have their own vibrations. All right, the chemical bonds that hold together atoms, they vibrate back and forth. All right, like springs. And so each type of water molecule, or each type of molecule has its own vibration and generates its own heat. It all has to do with the movement of water molecules. Right? Not just the vibration, but the movement. And these water molecules, or molecules in general, just colliding with one another, and it generates heat. Now, temperature is a measurement of the heat. It's a measurement of the vibrational energy and movement of molecules. In this case, we're talking about temperature, so we're measuring the movement of, for instance, water in a glass. All right, we're talking about the vibration of the water molecules and the collision of water molecules with one another. So, you talk about specific heat. Specific heat has to do with the ability to break chemical bonds, the amount of energy that's needed to break chemical bonds. All right, so think about a solid. All right, solid particles. Even in a solid, the atoms that make up that substance, they're vibrating, right? They have vibrational energy. But as you heat up that substance, the atoms, the molecules, begin to vibrate even more, and they begin to collide with one another even more, and spread out slightly. So there's this expansive process. So what you're talking about, for instance, is the ability to take, for instance, something like liquid water and convert it into a gas, for instance. All right, so liquids, the molecules, all right, they have their own arrangement. They're spread out, they're spaced, but they're interacting with one another, and they're forming and breaking new bonds. All right, but the ability to add energy to a system, such as taking a pot of water, putting it on the stove, turning the pilot light on, and heating up that water. All right, eventually the temperature of the water is going to rise to the point where you are beginning to break hydrogen bonds between water molecules, particularly on the surface. And those water molecules, as they're being broken from one another, they're going to transition into a gaseous state. All right, the molecules begin to spread out even further away from one another. All right, they're no longer colliding with one another because they're no longer contained in such a small space. So this process of high specific heat is also tied in with the process of evaporative cooling. All right, so on the surface, water surface, all right, you could be talking about boiling water, you could be talking about on the surface of our skin as we sweat. All right, as we sweat, you have water molecules that beat on the surface of our skin. And basically, as that water evaporates, you have heat that's being pulled away from the surface of the body. Or you have this transfer of heat. Because you are basically breaking on the surface of that water molecule, that droplet of water. You're basically breaking hydrogen bonds. So these water molecules can then escape. And as bonds are being broken, when bonds are broken, they are absorbing energy. And as they're absorbing energy, that energy gets transferred to that bond, it's broken. So this process, you sweat, you cool. Alright, so talking about the three states of matter, we're going to use water as an example because this part of the chapter is all about water. Alright, so you have water as a solid, you have water as a liquid, you have water as a gas. Alright, so notice here that as a gas, the water molecules are spread apart. Alright, they might collide with one another, they might form and break hydrogen bonds, but the likelihood of that happening is minimal in comparison to water as a liquid. Alright, so here as a liquid, water molecules are interacting with one another through hydrogen bonding. And so the water molecules are more compact and close to one another. Alright, but one of the very unique things about water as a solid is that it actually has a much more ordered structure. So here, notice that the individual water molecules, right, the individual water molecules have this specific arrangement. It basically has this lattice structure that it forms. In this case, the water molecules basically expand as they transition from a liquid to a solid. Alright, so water as a solid has a much more ordered structure, which is very important. Because notice that these individual water molecules are no longer as closely compacted as the individual water molecules in water as a liquid, which gives it very unique properties. Alright, so here you have an example of water going from being a liquid, right, closely compact, to the process of it freezing, becoming a solid. See this nice ordered crystal lattice structure that forms. Alright, so the ability of water as a solid, the fact that it expands as it freezes, is a very unique property to a solid. In this case, it becomes less dense as a solid than a liquid, right? Which is, in comparison to other substances that form solids, is pretty unique. All right, so one of the cool things about ice is that as a solid, water, since it's less dense, in a solution of liquid water, it floats. Because as a solid, those water molecules are arranged in a particular order, forming this crystal lattice structure. Alright, so since they're not as compact within a given volume, they have a lower density than water molecules as a liquid, which is more dense. Alright, so water is, as you can see here, temperatures below 4 degrees Celsius as water begins to freeze. The density of water decreases. And above that, it begins to become much more compact. Alright, so when you're thinking about density, density equals mass over a given volume. Alright, so basically it's thinking about how compact and close a substance is within a given unit of volume. Alright, so here you can see the units are grams per centimeters cubed, or grams per mil, or grams per liter. Alright, so the density of water is actually around 1. Alright, it's most dense at about 4 degrees Celsius. And so you can use this point of comparison of the density of water to other objects to determine whether or not those objects will, in fact, sink in a solution of water, or they'll float on the surface. Alright, so notice here that ice, alright, density around 0.9, like 0.98 or something like that. You'll notice that even though you have this small discrepancy, small difference between 0.9 and 1, it's enough so that ice floats in water. And it all has to do with the symmetry, the arrangement of individual molecules of water as a liquid and as a solid, which is all tied in with the ability of water to form hydrogen bonds. Alright, so when talking about chemical solutions and talking about solubility, alright, so solutions, chemical solutions, alright, you're talking about dissolving one substance in another. Alright, so aqueous solutions involve water as being the substance that something is being dissolved in. Alright, so a chemical solution is always going to have something called a solute and a solvent. Alright, so a solute is the substance that you're trying to dissolve. And a solvent is the substance that you're trying to dissolve your solute in. Alright, so it could be as simple as taking a packet of sugar and dissolving it in tea. Alright, that packet of sugar is your solute. The tea is your solvent. Together, your solute and your solvent make your solution, your chemical solution. Now, when you're talking about chemical solutions, if the solvent is water, it's always referred to as an aqueous solution. Now, when talking about chemical solutions, alright, there is an adage that states idea of like dissolves in like. Okay, so what that means is if you have a substance that is, for instance, polar, alright, water is polar. The substance, your solute, if it's polar, it will be soluble, it'll dissolve in water. Alright, because the chemical properties of those two things are very similar with one another. Okay. Now, on the other hand, you can have a situation where a substance is insoluble in a solution. Alright, so it's kind of like trying to mix, for instance here, alright, these are all hydrocarbons, chains of hydrocarbons. Basically, these substances are non-polar. They're non-polar, but the surrounding water molecules are polar. Alright, so you're trying to mix two different substances that have completely different chemical properties. Alright, they're not going to mix. Okay, so thinking about an aqueous solution. Alright, so in water, you're able to dissolve polar substances. Alright. You're also able to dissolve ions. Alright, so here you're shown an image of a salt crystal. Alright, so this is just a single little cube of salt. Alright, you place it in a beaker of water. Eventually, what's going to happen is your water molecules are going to begin to interact with those ions. Alright, remember that water has partial charges, and your ions have complete charges. Alright, so here you have your your oxygen atom, which has a partial negative charge. All right, that's going to interact with the positively charged sodium ion. And here you have your water molecule, the hydrogen atoms. It has a slight positive charge. It's going to interact with the negatively charged chlorine atom. Alright, so your chloride anion. Alright, so what happens is you get the formation of this basically a shell. What we call a hydration shell around each of your ions. So now, in this case, the ions are unable to interact with one another. Okay, so in this case, your salt has been dissolved. All right, that's what's taking place chemically as the substance dissolves. All right, you have these little hydration spheres that form around the individual components that make it up. So it dissolves or goes into a solution. All right, the same thing can be said for things like sugars and proteins. All right, later on we'll talk about these molecules in the next chapter. But you can have things like sugars, which are polar. You can have proteins, which have components of protein that are going to have charges or they're polar, and those parts of the protein can allow it to be soluble in water. Alright, so looking at pH. Alright, so I'm talking about pH. Your water is actually technically classified as a weak acid. All right, so what that means is that water can actually dissociate into ions. It'll dissociate into hydroxyl and hydrogen ions. All right, so here, your hydrogen ions are actually referred to as H3O plus, something that we call hydronium, but for all intents and purposes, all right, we're going to use the H plus. It makes it really simple. All right, so you have your acid H plus, and you have your base OH minus. All right, so two water molecules can basically, you have one molecule that donates a hydrogen, you have one molecule that receives it. All right, so in this case, one water molecule can give up a hydrogen atom, so it gets a negative charge, and another water molecule that accepts this hydrogen gets a positive charge. Alright, so when you're talking about chemical solutions, you're talking about pH. All you're talking about is basically a balance of either H plus ions or hydroxyl groups, hydroxyl ions. So here, in a neutral solution, all right, what that means is that basically the concentration of your acid is equivalent to the concentration of your OH ions. All right. Now, when you're talking about, for instance, an acid, in an acid, all right, you have a higher concentration of hydrogen ions. Alright, so that means that your concentration of hydrogen ions is actually greater than your concentration of OH ions. Alright, so you can get an acidic solution. And then when you're talking about a basic solution, it's the opposite. Alright, in this case, you have a higher concentration of OH ions than you do your hydrogen ions. Alright, it's all about balance. Alright, so looking at pH scale, for instance. Alright, so here, your pH scale, alright, notice that your pH scale goes from 0 to 14. Now, your pH scale going from 0 to 14. This is actually, in terms of increments, it appears like it's going from 7 to 8 to 9 to 10 to 11, 12, 13, 14, and it is. But in reality, this is a logarithmic scale. Alright, so it is a base 10 scale. Alright, so what that means is that, for instance, when you go from a pH of 7, right, to a pH of 8. Alright, you've gone down 1 unit, or gone up 1 unit in this case, but you've actually increased the amount of OH ions tenfold. Alright, so every increment is a tenfold increase in either OH or hydrogen ions, depending on whether you're becoming more basic or more acidic. Alright, so here, anything that is less than 7, alright, you're going to label as acidic. Anything that's above 7, you label as basic. Alright, so again, when a solution becomes acidic, alright, you are increasing the concentration of protons, hydrogen ions. And when your solution is becoming more basic, you're actually going to increase the amount of hydroxyl radical. You're increasing the concentration of hydroxyls, or OH ions. Alright, so for instance, looking at urine. You look at urine and look at black coffee. Alright, urine around a pH of 6, black coffee, alright, pH of 5, both of which are acidic. Alright, but the difference in the pH of the two solutions is, again, tenfold. Alright, a solution of black coffee has a tenfold higher amount of protons than urine, solution of urine. Now, when from urine to grapefruit juice, alright, again, you're becoming more acidic. Alright, so notice that urine has a pH of 6, and grapefruit juice has a pH of 3. Alright, so you're going 1, 2, 3 units. Alright, so you're becoming much more acidic, but in this case, it's not a tenfold increase. Alright, you have 10, 10, 10. Well, that's 10 to the third power, which equals 1,000-fold difference. Alright, so grapefruit juice has a 1,000-fold greater amount of protons than solution of urine. Now what about going from pure water to seawater? Alright, so here you're becoming more basic. Alright, so pure water has a pH of 7, and seawater has a pH of around 9. Alright, so you're going, again, it's a log scale, so you're going up 1 pH unit, 2 pH units. Alright, so 10 squared, which gives you 100 fold. Alright, so in this case, you have a 100-fold increase, not in protons. Alright, that's not the case. You have a 100-fold increase in OH groups. Hydroxyl ions. Alright, now going from pure water to milk of magnesia, pH of 11. Alright, so you're going 10, 10, 10, 10. Alright, so in this case, 10 to the 4th power. Alright, so 10,000-fold increase in OH minus. Okay, so talking about these fluctuations in pH. Alright, well, when you're talking about solutions, and you're talking about solutions in living systems, alright, it's very important that these solutions, for instance, like blood, that it remain within a certain set of parameters. Alright, there's certain parameter for the amount of acid or base. Alright, so the pH. Alright, the pH needs to be within a certain range. Alright, so if you go back and you look at, human blood, it's slightly alkaline, but just slightly so. Alright, and so the body has to maintain this pH balance. Alright, and it does this by using a series of different kinds of buffers. And there are all kinds of buffer systems in the human body. Alright, we're only going to talk about one type of buffer system. Okay? Now, what exactly is a buffer? Alright, well, as the name implies, alright, it's preventing a change, or at the very least, it's trying to minimize a change. Alright, it's kind of like a series of bodyguards, or a link chain of military personnel that are trying to keep people from getting into a certain area. Alright, you can have this push on this border, on this buffer, and it's trying to mitigate and minimize the amount of people that are coming through, right? But eventually, it is going to weaken. That barrier weakens, and it'll just burst open, and in this case, the pH will change. All right. In this case, people can enter this restricted area. All right. So when you're talking about a buffer, all right, you're trying to minimize the change in pH. All right. So a buffer does two things. A buffer is going to accept protons, all right, when they are in excess. All right. So this would be when the pH of a solution, like blood, becomes too low or acidic. Alright, so if the pH of blood is becoming too acidic, alright, by picking up excess protons, because it's the free, alright, it is the free protons that are actually affecting the pH of the solution. Alright, so what's happening here is that the excess hydrogen ions that are causing the pH to drop, alright, or they would, your buffer is basically picking them up, is accepting them. So it's basically removing them from the solution. Alright, and then let's say, for instance, the pH of the blood becomes a little bit too alkaline. Alright, it's going to do the opposite. In this case, it's going to donate protons back into the solution. So basically, since the pH here is becoming too high, alright, it's becoming more basic or alkaline. Alright, what the buffer system is trying to do is, by releasing protons into the solution, is trying to adjust that pH back to its normal range. Alright, so it's all about trying to keep everything in check and everything balanced. Alright, so here, talking about a specific buffering system in the body. Alright, so we have our base form, bicarbonate, and we have our acid form, carbonic acid. Alright, so we have our base and we have our acid. Alright, so here, if the body fluid, alright, the blood becomes too acidic, alright, since it's becoming too acidic, there are too many protons, alright, so these protons are going to be picked up by bicarbonate, which is our base. Alright, and in this case, you're going to form carbonic acid. Alright, so this is so that the pH of the blood, for instance, would go back to normal. Alright, so the bicarbonate ions pick up excess protons to form bicarbonate. Right, now, what happens if it becomes too basic? Well, if it becomes too alkaline, your bicarbonate can release protons back into the solution, back into the blood, so that the pH drops back towards its normal pH range. And as a result, basically, this carbonic acid is what it's doing. It's dissociating. All right, is breaking apart. All right, so it's dissociating into your proton and your bicarbonate ion. All right, now this is a balancing act. Okay, so this is all about having a chemical equilibrium. and keeping everything in check. Alright, so it's all about trying to keep the pH at its normal set range. Alright, so as like all chemical reactions, alright, by increasing the amount of protons, alright, looking at it from left to right, reactants on the left, products on the right, if you increase your protons, alright, as a reactant, you're going to have more collisions and interactions with your bicarbonate ion, and you're going to form more carbonic acid. You're going to form more product. Alright, now this is within a given amount of, you have a set amount of bicarbonate, and you're going to produce a certain amount of carbonic acid, alright, by dumping more protons in. Eventually it's going to reach a threshold, alright, where you've basically used up all of your bicarbonate. Alright, so you won't form any more product after that point. Which in this case would cause the pH of that solution to actually fluctuate and become more acidic. Alright, so buffers will eventually break down. Now, the reverse reaction can take place, where your carbonic acid can dissociate back into a proton and bicarbonate. It's all about a balancing act. Alright, trying to keep pH in balance in its given range.